Hey guys, welcome to another episode of Build Tensorflow. I know it's been a long time since the last episode, but let's correct that with this one. So a lot has happened actually since the last episode. We were finally able to train our first model, so that's really exciting stuff. We trained a Celsius to Fahrenheit converter, and we backpropagated, and it all worked fine. So let me just show you guys about this stuff. Let me just commit this. One second. Alright, so where were we? We were at dataset. Okay. Alright, so let me just increase the font. That's too much. Okay, that's fine. So what's changed? What's changed since the last time? What did we see last time? Last time, what did we see? Let's check our YouTube. Actually, I don't remember what we did last time. So as you can see, Game of Thrones just came out, so I've been watching that. Okay, GPU programming, right? So, and backpropagation of the dot product. Alright. Okay, so okay. So now alright, so what's changed is there's a new optimizer. I've coded the synchronous gradient descent, and there's another new thing in layers called the dense layer or the fully connected layer. So that's new. And so another new thing is the data folder, which has a new data loader and a data set. The data set that we have currently is a Celsius to Fahrenheit data set. As the name suggests, the input is some values indicating that they are values in Celsius degrees, and our targets or our ground truth is Fahrenheit. Those Celsius values convert to Fahrenheit. So this is just sanity check on the framework that the backpropagation is working well and we are actually able to train. The other thing that's new is what else is new? We just made a little bit the code a little cleaner. So we have a vector.h, which has the overloads for all vectors, subtraction, addition. Similarly for tensors has an addition, a division, a multiplication with a scalar and a tensor, sigmoid and power, right? Not much. And then operations has the sigmoid operation, the power operation, the operation that you saw last time. Nothing new here. MNIST is, you can ignore this for now. That's what I've been working on for now, like trying to train the MNIST data set on this framework. Alright, I think we can dig in now into the code. So what's new is, let's look into our main file. So this is the first time our framework is actually trained on a data set. So here we load the data set. So the way the data set in this project data sets or data loaders will work is you initialize the data set according to whatever it is, and you run this create kind of function. And if it's a data set that in which the values are created and not imported, such as images or text, so in this case we actually create some new values, some random values. So that's a create function is here. So let's dig into what Celsius and Fahrenheit is. So it's pretty straightforward. It inherits from a class called data loader. Let's just go into data loader. Yeah, so this is the base class for all data sets in this project. So we have a data vector which has a pair of input and target as specified here. opportunity to actually comment some code. Alright. And then there's a virtual function called add that we have to overload in our inherited classes. So this function, what it does is basically adds the data to the dataset. That's all. I guess we should also have another function called get, but that's not we don't have that as yet. So here is what we do here is. So this is just plain, this is just a converter, a Fahrenheit. This is the formula to convert Celsius to Fahrenheit, and we just push back, we overload this function. So we just push back and make a pair of input output. We get our input output here, and in a create function actually calls this add function, where it iterates over how many examples we want, and then creates a random input and target, and then just adds it. It's pretty straightforward. So that's our data loader, and back to our main CPP is here we can create our own model. So this is just a fully connected network with one hidden layer. So the input is one input is of size 1, and the output is also be of size 1. So as you can imagine, our weight matrix is 1 by 1. So that's just that indicates that we just have one hidden neuron, and we actually don't have an output layer. Our hidden layer is our output layer here, and we specified that we don't need activations. And so I'll go into the dense layer now. Dense layer is pretty straightforward. It's just a fully connected network, and for those whoever knows what a fully connected network does, this might look really familiar. So here we have our input size and our output size. Depending on that, we initialize our weight matrix of our input size and output size. Here we initialize our weight matrix according to some scheme. So you can either initialize all your weights to be 0 by default, which is really bad, and it won't ever train because there is no stochasticity to the data. And so generally you want your weights to be tiny, and at the edge of and a little bit unpredictable. So you generally have the weights centered around a mean of 0, but the standard deviation or variance should be dependent on how many inputs are coming in, and how much do you what output size do you want. So that's generally called the fan in and the fan out. The fan in is the number of inputs coming in, the fan out is the number of outputs being generated. So according to that, some people have come up with various formulas that tend to work well. So one of those initializations is called the Glorot initialization, and that's been known to kind of work well. So I've just made the Glorot initialization. There's a fan in and a fan out, and that's an innovate, and there's a function utils. So what this does is the mean is 0, and we sample from a uniform real distribution which has a variance of 2 by fan in by fan out. So this is the formula they come up with. If you guys are interested, you can go read this paper. It's pretty good. So what these guys understood, that it's typically really difficult to train deep feed-forward networks if the initialization isn't great, and generally what happens is that you suffer from vanishing or exploding gradients if your initialization is kind of wacky and not well distributed. So these kind of initializations help in reducing those vanishing or stale gradient problems. Generally want your distribution to be thick around the center and evenly distributed is something. This is a really nice article on Medium which goes into details, and you guys can look that up if you want. So there's a question whether to use a uniform distribution or a normal distribution to sample from. We currently use, I think there are two schools of thought. One is the Hinton thought, which uses a normal distribution, and the Bengio school that uses a uniform distribution. There was a really interesting pull request on Keras that delved into this. So I'm using a uniform distribution as that's known to perform better according to the creator of Keras, Francis Chauvet. So I've just used this. It's really easy to do in C++. You just initialize the generator, and then you initialize the uniform real distribution. You give your mean and standard deviation, and then you just run this however many times you want, and that generates a sample, and you just push it into the weight matrix. Pretty standard here. And so now, after we've initialized our weights, we can just talk about the variables in our fully connected class. You generally have your weights, right? So that those are generally trained to get better, and your biases, right? And those are also trained to get better. These are initialized to 0, and then you have your input size and your output size, and then you have the activation you want to feed into. So generally what happens in a fully connected layer is you dot product your weight matrix with your input, and then add that result with the biases, and then run this entire the entire result and squeeze it into a non-linearity, whether it's a ReLU, a sigmoid, or a tanh. So to non-linearities are how neural networks are able to build these really complex function approximators. Otherwise, if there were no non-linearities in a neural network, it would just be quadratic or a quadratic or a linear equation, right? So the non-linearity forces it to do some weird things. That's a really bad explanation, but that's what I understand from it anyway. And so forward is the function that we generally write a forward pass of anything in this framework, kind of like Pytorch. So here we do the dot product, we then add with the biases, then we have our logits, which we run them either sigmoid, or if there's no activation, we just give this to the logits and we return our logits. Right, so that's done. Dense layer is clear, and that rhymes. Then let's come into the optimizer. So what our optimizer does is that it's basically after our gradients have been computed. That means after you've run dot backward on your loss tensor, and the partial gradients have been calculated for all tensors. The stochastic gradient descent, what it does is it just finds out all the tensors that were involved in your forward propagation in the network, and then just steps through one step of the weight updation, where it updates the values according to the gradients being calculated. So the weights of your network are adjusted in the right direction to predict what you want it to predict depending on your training data. So let's step into stochastic gradient descent. Stochastic gradient descent inherits from a class called optimizer, which is a generalized class which has a unordered set called balance. It's a set because we don't want to put the same tensor twice in there, so I just added an unordered set. That could happen if you're working with a complex network, and it's unordered because it will work like a hash table, and if it's a normal set, it will work like a hash map. That's kind of slower. That's log n, and this is O of 1 retrieval time. Then we have a learning rate. So every optimizer does have a learning rate. And then we have a function called zero grad. This is really important, as after you've updated your tensors with the partial gradients, the values of the partial gradients, and you updated your weights, you want to initialize all the gradients back to 0. So that's where this comes into play. And the step function is function that's meant to be overloaded according to what optimizer you're writing, which basically informs how the weight updation should take place. So in this case of stochastic gradient descent, it's pretty clear. What it does is okay, so let's go step by step. So the step function is called by the minimize function, and minimize function is actually what the user will interact with. The user will just say sgd dot minimize and then put the loss in here. and then it will just minimize the loss and update our tensors. So what it does is, the first step, it gets all the parameters, all the ways that are involved in the forward propagation of the network. Once it does it, it runs a step call where it steps through all the tensors, all the parameters, and just does this, which is t-val minus learning rate, where you step in the opposite direction of the gradient to minimize it, and yeah, that's, you just multiply with the gradient, and that's how other values become better. And then you reset all gradients to 0. That's about it. And then you clear the parameters at each step. Okay. Alright, so once this is done, so that's a stochastic gradient descent here. So let's run through the training loop. I have purposely not added the get function from our dataset because I wanted it to be kind of flexible. However the user would like to use it. So this is running for 2000 epochs here, and then it's stepping through the entire dataset in this loop. Quite clear for some user, quite intuitive, right? And then you get your data like this. So the first in the pair is the input, the target is the second, and given our sizes 1:1, 1:1, and then we run our input through the network, we generate our prediction, then we calculate our loss, which is, right now I haven't made specific loss functions like mean squared error, binary cross entropy, negative log likelihood, and all that stuff. So this is just a very bare bones. So for the loss, we have we multiply the target with negative, and then we add it. So that's basically the error and loss, or prediction minus target loss. Prediction minus target, and loss equal to y squared. That's what's happening here basically. That's a final loss, which is the square of the prediction of the absolute error, not the absolute error, just the error. And then we just run a backward. This is the best thing about our framework, is that to compute our gradients, just run the backward call, and this will do it recursively right here for now. After you've calculated all your gradients, just minimize the final loss, and it will just step through everything and train your network. And we can see that the loss is reducing. So let's try to run this. You guys will see the magic happening. Right, you can see the loss has come down to something 0.09, and then this is the inference. The conversion of 4 degrees Celsius to Fahrenheit is 39.2, and guess what? This is our output value, the value that has been outputted from our network. This is not any target data, and this is indeed minus 39.2. If you want to see something, if you want to find the Celsius of say 10, so 101, 110, right? Let's see it, and then right here, so 110 Celsius to Fahrenheit. That's 230 Fahrenheit, not 230.003. It works, right? It works. So that's all, and I've also actually added a little code for removing memory leaks. So you can actually call delete on the final loss, and that will recursively delete all the tensors, or try to, and all the ops. So here, once you come into the destructor, it deletes the back op. So once it goes into the back op, it actually comes right about here, and then it deletes T1 and T2. So, and that just goes on and on and on until there's no T1 and T2, right? So that's pretty cool. So that's where we're at right now. We're able to finally train a small network with no non-linearities or anything like that. Now we want to go on to bigger and better things like MNIST, and then see if we're able to train a network on MNIST and also run it on the GPU. So for MNIST we need a few more things. We need the softmax function for because it's essentially a classification problem, and we'll probably need softmax, a cross entropy loss. So two things there, and I think the capability to average over a mini batch is good because we want a big mini batch for our training. Because training on a mini batch of one will take a really long time, and sometimes it doesn't train because once you have a mini batch and you average the gradients, it gives a truer approximate of the real gradient of the real true direction that you want to go, whereas a single examples can be a bit noisy and it takes a long time to train. So we need proper mini batch support. So that's what I'll be working on for a bit, and just wanted to give you guys an update of what's been happening with this project. And we're picking up pace, and we finally have something to show for. Especially this API is so nice, like you can just run backward and it just works. So now I suggest guys, if you're interested in this project, you should definitely check out the GitHub and the pull request and our project section in our GitHub projects. So if you guys are interested, okay, yeah, it's finally opening. Internet is a bit slow right now. And you should definitely check out. So we're at 50 commits yet, and each of these commits are pretty like the commit messages aren't really bad, but they aren't really good either. But the good thing about the code is that I've tried to document as much as possible. So even if you go into any random like a dot product implementation, you'll find some comments saying, so this is the back propagation of the dot product, and what everything means, and what's the use of each file. Let's say, so for example, weights.h, utils for weights, different weight initialization schema for decluttering weights in the future. So that's something. So it's something. It's not nothing. So it gives you some idea. So if you go into the main file, so you'll get a lot of documentation here, like what exactly this file aims to do, a lot of documentation above the function headers, and this is meant for newcomers to understand the code, make it readable. So, and if you guys really interested in the future, we track our issues in our projects. So right now we have a bunch of things to do. We need to add a dropout layer, batch norm layer, loss layer, and subtraction and average operation is currently pending. We need to do that. And there's GPU code addition I've added, but surprisingly running on the GPU on this project is not faster than running on the CPU. I don't know why actually. I think the memory loading and unloading time or put data on the to and fro from the GPU is a really big overhead, and takes a lot more time. What else is left? So we've closed a bunch of issues. We've done with the dataset layer and optimizer layer, successful training. So this was a big pull request that did all of the above that I just showed you before. So if you guys are interested, just check out the pull request. Almost all of them are well documented, and what we aim to do with each pull request. So it's not something that you won't know what's happening. So for example, if you go into a random pull request, this has got 32 comments. I don't know why. That's a lot of comments, I think. So for example, it just says what all happened in this pull request. Yeah, so definitely check this out. I'll leave the link below, and see you next time, guys. Then next time we'll probably be able to train MNIST well, completely from scratch, and in the future we'll probably need some way to save our weights and resume training, because for these small networks it's fine, you can run and train again and again, but for big networks you want the capability to stop and restart training on the go with just one command line, not really changing the code. So that's one thing where we need to add some kind of serialization and deserialization of our models. What else? What else is needed? So after that we're going to only work on MNIST. We're not going to touch any other data set, and we're going to run convolutional neural networks on MNIST. Then maybe try a GAN network. Let's see if that trains. Right. I did train a GAN network on Cypher on this machine, so the GPU can handle it, I think. So that would be quite interesting if we are able to train a GAN here just on MNIST data. So but the main plan is just train MNIST for now, train it to 97, 98, 99% success rate, whatever the norm is, and then try to better it with convolution neural nets, and drop out whatever residual networks, whatever. Okay. Alright guys, see you next time. Hope this was informative and fun for you. Alright, bye bye.